In February of 2019, the leader of the National Chamber of the Transformation Industry in Mexico issued a critical warning. The Federal Electricity Commission and the federal government face significant challenges in meeting the country's growing energy demand. With a landscape shaped by population growth and economic development, it was highlighted that without significant investments and collaborative efforts with entrepreneurs, regulators, and private initiatives, Mexico could face a critical energy shortage by 2022. These concerns quickly materialized. Just a few months later, during March and April of 2019, the state of Yucatan experienced power outages that exposed the fragility of the national electricity system. Ironically, despite Mexico's strategic location and ideal climate conditions for harnessing renewable energy, such as solar, electricity generation continues to depend primarily on oil. So we ask ourselves, why continue down this path? Why not take advantage of the benefits of our location to address this issue? Starting with the devices that see the most use in any society, lamps, and the region's predominant energy source, solar power. Our primary goal is to help resolve the energy shortage while exploring sustainable solutions that possibly impact vulnerable communities. To achieve this, we have structured our objectives in three main phases. The first one was the understanding of the landscape and solar potential. We focus on analyzing the current situation and the potentials for solar electricity generation in Mexico. This includes studying the basic principles of photovoltaic systems and using measuring instruments to evaluate factors affecting their performance, such as series and parallel configurations. The second phase was designing and developing practical solutions. In this phase, we concentrate on understanding solar cells and applying this knowledge to design and assemble practical circuits that integrate photovoltaic modules, rechargeable batteries, and LED lamps. We also identify key factors such as location and orientation to optimize system performance. And the third phase was implementation in vulnerable communities. Finally, we bring our solution into a real-world setting by installing a photovoltaic lamp in a community in need. This not only validates the technical functionality of the design, but also fulfills a social commitment, directly improving the quality of life for residents. Additionally, we evaluate its performance under real conditions to ensure its efficiency, durability, and long-term adaptability. Let us begin by understanding some basic concepts that will aid in the development of the project, starting with the question, what are photovoltaic lamps?
Solar lamps are an innovative and sustainable solution that uses solar energy to provide lighting in areas that lack access to the electricity grid. We will explore the basics that are fundamental to the development of these lamps, especially for communities in need. Solar energy is one of the most abundant and clean energy sources available. It can be captured even on cloudy days, making it a viable option for various regions. Solar panels, which are the basis of photovoltaic lamps, convert sunlight into electricity through the photovoltaic effect. This process involves the excitation of electrons in semiconductor materials, thus generating an electric current. There are three key components in a solar lamp: photovoltaic cells, charge controllers, and battery. The photovoltaic cells are the heart of the system. They are composed of two layers of semiconductors, an N shell, which has an excess of electrons, and a P shell, which lacks electrons. When sunlight hits these cells, electrons are released, creating a flow of electricity. Then the charge controller is essential for regulating battery charging. It prevents overcharging and over discharging, which is crucial for extending battery life and ensuring optimal system performance. And then there is the battery. The battery stores the energy generated during the day, allowing the lamp to operate at night. This is especially important in communities where electricity is not available, ensuring that lighting is available at all times. There are also a few benefits with the solar lamps. The access to clean energy is vital. Photovoltaic lamps provide a source of illumination in vulnerable communities, improving the quality of life by allowing nighttime activities such as studying and working and socializing, all this without generating carbon emissions. Then there is sustainability. By using solar energy, dependence on fossil fuels is reduced, which contributes to the mitigation of climate change and minimizes environmental impact. In addition, these lamps do not emit polluting gases, which improves air quality. And at last is the reduced cost. In the last decade, the cost of manufacturing solar panels has decreased significantly, making these solutions more accessible and economical. This allows for communities to benefit from solar energy. Implementation. For photovoltaic lamps to be effective, it is crucial that their designs and aesthetics ensuring that they integrate well in the local environment. In addition, training the communities in maintenance and use of the systems is critical to their long-term sustainability.
With the latter in mind, we move to the phase 2, the creation of our prototype, but first we have to make a decision of how to assemble our circuit, that would be the essence of our lamp. To make this decision, first we evaluate 3 different circuits. Circuit 1 is a solar system that uses solar panel and a chargeable battery. This design allows the lamp to charge during the day and work automatically in the night thanks to the light sensor. This circuit proved to be the most efficient in terms of energy and functionality. By the other hand, Circuit 2, an automatic night lamp, used a timer and a microcontroller, although it was easy to assemble. It lacked a light sensing system, making it less suitable for continuous outdoor use. Finally, the Circuit 3, which also used a timer, showed a constant power consumption, but it was not ideal for our needs, as it did not adapt to the environmental conditions. After analyzing the advantages and the disadvantages of these circuits, we decided to go with the Circuit 1, as it combines energy efficiency and automatic functionality, making it perfect for the nighttime use. In order to assemble this, the following materials were used. Solar panel. We use a 5 volts and 160 mA solar panel. This size is adequate to ensure that you can charge the battery efficiently during the day. Rechargeable battery. We opted to set off the 9 volts rechargeable batteries. These batteries are known for their high storage capacity and durability, allowing the lamps to operate during the night. Transistors. We use 2 NPN transistors, T2 and T3. The T2 controls switch on and off the lamp based on the ambient light, while the T3 acts as a second switch that allows the battery power to flow the LEDs when there's not enough light. Resistance. We have 3 types of resistance. A 1 kΩ resistor, which limits the current to the T3 transistor. A 4.7 kΩ resistor, which controls the current to the T2 transistor. And a 680 ohm resistor, which protects the charging indicator LED. Capacitors. We use capacitors to stabilize the voltage in the circuit, ensuring smooth operation and protect the most sensitive components. LEDs. We choose energy-efficient LEDs, especially a green LED to indicate the state of charge, and a set of white LEDs for the lighting. LEDs are ideal for this type of application, as they consume little energy and have a long lifespan.
As for the housing, we decided to design a simple and functional structure that protects the circuit and batteries from inclement weather. The housing is made of plastic, a material that, although not the most sustainable, offers the durability needed to withstand outdoors conditions. The housing includes a space for the solar panel at the top, ensuring that it receives maximum sunlight. It also has holes for the LED lights. It's equipped with a diffuser to ensure uniform illumination. In addition, We have incorporated a LED indicator that shows when the system is in charging mode. The structure is designed to be easy to hand on any surface, and all components are firmly secured in place to prevent movement or vibration.
During the field test with the PV lamp, we collected key data to evaluate its performance in real-world conditions. We analyzed metrics such as charging efficiently solar panels under the different levels of radiation, the durability of the control circuit and rechargeable battery, as well as the average lighting time in the provides night. In selected communities such as Tlanepantla and Atizapán de Zaragoza, the test reflected the lamp's ability to adapt to the real needs of the users. In Tlanepantla, where the power outages are frequent, lamps proved to be a reliable source of illumination, operating stably throughout the night. On the other hand, in Atizapán, we evaluated its performance in advantageous conditions such as cloudy days, verifying that the battery continued to provide the light despite the limited solar generation. In addition, we document users' experience with the interviews. Residents cited significant improvements in the nighttime safety and noticeable reduction of expenses for the alternatives such as candles and kerosene lamps. These tests not only confirmed the technical feasibility of the PVM lamp, but also gave us valuable information to host this design and ensure that the response to the daily needs of the vulnerable communities. The implementation of photovoltaic lamps not only represents a technical advantage, but also an opportunity to transform lives and vulnerable communities. By leveraging solar energy, we demonstrate how to innovation can address critical challenges such as energy shortages, providing sustainable and accessible solutions. This project underscores Mexico's potential to lead in renewable energy, given its excellent climate and growing need for clean energy alternatives, by combining technology functional. Thank you very much, and we will see you the next time. See you.